In this part, we learn about how to represent real numbers in a computer. Now, what is a real number? A real number is any integer or a rational or an irrational number. Basically, any number that is not a complex number is a real number. Typically, we can think of a real number as a number having an integer part and a fractional part, alright? Let's take an example. A real number like 453.14 can be written like this in the decimal number system. Now here 453 is the integer part, whereas 14 is the fractional or the decimal part. And these two parts are separated by this point, which is called the decimal point. And if we were to write this number in powers of 10, this is how we do that, okay? So you may be knowing that the decimal number system or the binary number system are positional type of number systems, which means that the value of a digit in the number depends on the position of that digit. And we say that each position has a weight of tens or hundreds or thousands in case of decimal, or ones or twos or fours and eights in case of the binary number system. Now notice that the fractional part is written in negative powers of 10, starting with 10 raised to the power of minus 1. Then the next term will contain 10 raised to the power of minus 2 and so on, decreasing weights as we move to the right by a factor of 1/10 or 1 by 10. So this was in the decimal number system, which we are used to quite well enough. Now let's apply the same idea to the binary sequence 1.1. Because of this dot or point, we are sure that this number must have some fractional part, okay? And this point is called the binary point because we are using the binary number system, all right? And the way we can represent this number in powers of 2 is this. We use 0 or greater powers of 2 for the terms on the left side of the binary point, which represents the integer part, while the fractional part represented by the digits on the right side of the binary point come with negative powers of 2, starting with -1 and then -2 and so on. Because of the binary number system, we already know that we use the powers of 2. Okay, the new thing for some of you might be the negative powers of 2 for the digits representing the fractional part. Now to get used to it, I suggest that you write the expanded representation in powers of 2 for a couple of binary fractional representations. So in our example here, the decimal number represented by this binary sequence is 1.5, okay? So a binary 0.1 represents a decimal 0.5, a binary 0.01 represents a decimal 0.25, because that's 2 raised to the power of -2 or 1 by 4. And similarly, a binary 0.001 represents a decimal 0.125 and so on. So every time we move by a digit to the right, the weight of the position gets halved. Obvious, isn't it? Now let's take another example. 101.111 in binary. Now what is this number in decimal? We do the same thing, raise the digits to powers of 2 according to the weight of the position of the digit. So this represents the decimal number 5.875. You may want to pause the video here and try this exercise, just to make sure you are following along. And the answer to this question is 13.625, which is option 2, okay? Now that we understand how to represent real numbers in the binary system, let's see how can we represent these in a computer. Now the first thing which is quite obvious is that we need to say how many bits shall we reserve. And although 8 bits is not enough to represent real numbers, and you will see why later, let's use it for the sake of ease of our calculations and understanding. Now a real number can be both positive as well as negative, but 2's complement math does not work for real numbers, okay? So we don't use 2's complement. Instead, we use the sign magnitude to represent sign and magnitude of the number. So we use the leftmost bit as the sign bit, where a 0 means positive number and a 1 there represents a negative number. And because we use sign magnitude to represent real numbers, the rest of these 7 bits are the magnitude bits, okay? So let's see how we can store this binary real number in these 8 bits. Since the number is positive, the sign bit stores a 0. Now, how to store the magnitude? Well, we will have to make some assumption about the integer and the fractional parts. We can choose as a convention that the next 3 bits after the sign bit will represent the integer part, and the last 4 bits will be used to store the fractional part. So let me just change the colors for clarity. So the blue color bits contain the integer part, while the orange ones contain the fractional part. And of course, in reality, the bits are not colored, okay, in case that is confusing you. We are just using colors for our understanding. So now the integer part goes on the blue side and the fractional part can go to the orange side. And all these empty bits can be set to 0. Now this seems like an alright way to represent real numbers, isn't it? Now this way of representing real numbers is called fixed point representation, because the binary point is conceptually fixed in the bit sequence. Now let's represent these numbers on a number line, because that gives a quick pictorial view for better understanding. This bit sequence represents a 0.0, right? So let's mark it on a number line. Now what's the next real positive number that can be represented in 8 bits? The one represented by this bit sequence, okay, just like an odometer. Now this must be raised to the power of -4, okay, which is 1 by 16 or 0.0625. So let's mark it on the number line. Now what is the next number? Now this sequence is 1 raised to the power of -3 or 1 by 8 or 0.125, and we mark it on the number line. The next one is this, which is 2 raised to the power of -3 plus 2 raised to the power of -4 or 1 by 8 plus 1 by 16 or 0.1875. And we keep running the odometer until we reach the number just before 1, which is represented by this bit sequence, okay, which represents the number 0.9375, and the next number is 1, okay, the first integer after 0. Then the next number will be 1.0625, and we go all the way up to the max, which is represented by this bit sequence. 0 in the sign bit representing a positive number, while all the magnitude bits being 1 represent the largest positive number, and we can calculate its value to be 7.9375, and let's just mark it on our number line. Now on the negative side of the number line, we should get a mirror image of the numbers, because the only thing that will change is the sign bit, which will be 1 for all the negative numbers. Also, the difference between each of these numbers is going to be 0.0625. So all the numbers are equally spaced on the number line. Now, this is a very important thing to remember, because when we talk about floating point numbers, we will see that the spacing between the numbers is not even, or it's not equal. Now in 8 bits, we cannot go beyond this number, which looks kind of small, given that we were able to represent -128 to 127 in signed integers or 0 to 255 as unsigned integers. So how do we represent larger numbers? Well, we can just use some more bits. Let's check the largest number that we can store in 32 bits. So in 32 bits, after the sign bit, we can use 15 bits for the integer part and the next 16 for the fractional part. So now the largest number that we can represent is this. Now this number is also not very large, and if we use more bits for the integer part to get to larger numbers, we would do that at the cost of fractional precision. For example, how would you represent really small numbers like the size of an atom and so on? Anyways, let's try 64 bits. Now in 64 bits, this is the largest number that can be stored. It's just about over 2 billion. Again, not very large considering that we are using 64 bits. So by using fixed point numbers or representation, we are compromising on both aspects of the number. How large a number is dictated by the integer part, and how precise is it dictated by the fractional part. Now, one thing that is of interest is we want to be able to store very large numbers. We also want a high precision or be able to represent very small numbers, then of course all the other regular real numbers. Now the interesting thing is that if we have a number which is very large, it doesn't have to be very precise practically. For example, if we say that the distance between the Earth and the Sun is so many billion kilometers, we don't worry about a few centimeters here or there, right? Or if one says that Bill Gates or Warren Buffett have about $50 billion, we don't need to know how many cents they may have on top of those billions of dollars, right? The point is, when we deal with large numbers, we don't need a whole lot of space for the fraction part. Which means that in our representation of numbers, there can be a way such that the binary point can move or float depending on the number we are representing. That is, for small numbers or for higher precision, we can borrow bits from the integer side, or if we want to represent large numbers, we can borrow bits from the fraction side, which makes it look like as if this binary point floats about the bit sequence. Now this way of representing real numbers is called floating point representation, and we will learn that in the next part. Thanks for watching.